We now begin our discussion of hypothesis testing by looking specifically at tests for means. So we'll start here with the one sample test for the population mean mu.
Recall from the last chapter that a hypothesis test is a statistical procedure to decide if the given hypothesis is true or false. This procedure usually involves the following elements. First, we'll state the null and alternative hypotheses, specify the risk level alpha associated with the test. Then, we'll use the sampling distribution of the appropriate test statistic to determine the rejection region, also known as the critical region, and we want this rejection region to have size alpha. Recall, this rejection region defines values of the test statistic for which the null hypothesis should be rejected in favor of the alternative hypothesis. Then we'll compute the test statistic based upon the sample data. And we want to keep in mind that the test statistic here is going to measure the standardized discrepancy between the claim under the null hypothesis and the evidence observed from the sample data. Then we'll make a decision. Let's look at an example. What is the average body temperature for a healthy adult? Most people would argue 98.6 degrees Fahrenheit. However, in 1992, researchers from the University of Maryland published a study arguing that perhaps we should reject the common belief that average body temperature of a healthy adult is 98.6 degrees Fahrenheit. In fact, in their survey of 106 healthy adults, the mean body temperature was 98.2 degrees Fahrenheit with a standard deviation of 0.62 degrees Fahrenheit. So what we're interested in determining is whether or not the sample data provide enough evidence to suggest that the mean body temperature differs from 98.6 degrees Fahrenheit. And we'll do this test at the 5% significance level. So first, we want to define our hypotheses and specify alpha. Our null hypothesis should be our common belief that the mean body temperature is 98.6 degrees Fahrenheit versus the alternative hypothesis that the mean body temperature differs from 98.6 degrees Fahrenheit. And since we're testing at the 5% significance level, then that tells us that alpha is equal to 0.5. Since the claim is made about the population mean, the sample statistic most relevant to this test is the sample mean, which states that x bar is 98.2 degrees Fahrenheit. As a result, we're really interested in looking at the distribution of x bar, and so since our sample size is large, greater than or equal to 30, the central limit theorem applies. Therefore, we know that x bar has a distribution which is approximately normal. In other words, when we compute our test statistic, we'll be computing a z-score. As such, that tells us that we're going to be performing a z-test procedure. So let's first determine the critical region. Since we know we're going to be performing a z-test, then that means we're going to construct our rejection region based upon the z-distribution. Also, when we look at the alternative hypothesis, which states that mu is not equal to 98.6 degrees Fahrenheit, we'll use that to tell us that we're doing a two-tailed z-test. So then what we're going to do is we're going to take the z-distribution, and we're going to take that area alpha, and we're going to chop it into two equal pieces, alpha over 2, and we'll chop off area in the left and right tail, each equal to an area of 0.025. So our rejection region will correspond to z-scores that sit in these tails here. In particular, if we look up the z-table and we look for the z-score that has an area of 0.025 in the right tail, we'll find that z-score is 1.96. In other words, our rejection region is going to be the set of z-values for which the absolute value of z is greater than or equal to 1.96. That corresponds to z-values greater than or equal to 1.96 and z-values less than or equal to negative 1.96. Next, we'll compute our test statistic, and we know that if we want to compute a z-score, we're going to take x bar and subtract the mean and divide by the standard deviation over root n. However, in this case, we don't know the standard deviation for the population. As such, we're going to use the sample standard deviation as an estimate of the population standard deviation. So we'll take x bar, which is 98.2, and we'll subtract the mean, and the mean that we're subtracting is the value that we're assuming is the mean under the null hypothesis. Then we'll take our sample standard deviation and divide by the square root of the sample size, and we'll produce a z-score of negative 6.64. Now here's our decision. This test statistic, z equal to negative 6.64, lies in the rejection region, since negative 6.64 has an absolute value which is greater than 1.96. This means that we're going to reject the null hypothesis in favor of the alternative. So our conclusion is that evidence suggests that the mean body temperature of healthy adults differs from 98.6 degrees Fahrenheit. The inherent danger in the above argument is that the test does not provide proof that the original assumption was wrong. We have merely shown that there is evidence to support the belief that mean body temperature of 98.6 degrees Fahrenheit may be incorrect. We must acknowledge that the sample mean of 98.2 degrees Fahrenheit may have happened by chance.